Hello. So I thought in advance of the labs I'd record one or possibly more tutorial videos. The reason being that there's often the same things have to be gone over in person. So I normally spend a little bit of time explaining in the lab room, how certain things work and certain things you need to know in advance of the lab. And I thought, hey, why don't I put that in a video? And then people can watch it at their own time, or they can revisit if they don't understand. And so and then I thought, hey, instead of a video, why don't I do a little bit of coding as well? So you can kind of follow along, pick up not just the necessary information, but perhaps a little bit of the skill required in terms of like debugging and stuff like that of it. And so what I've done is I've just spent 2 seconds or 30 seconds setting up a problem. And so what this problem is I want to solve a differential equation, because effectively that's what the solar system simulator is you're solving a set of differential equations that in order to predict the future evolution of the solar system. And so in this case, instead of that, I've gone for a mass on a spring, which is the simplest differential equation I can come up with. So in here, what you're looking at is my text editor, my development environment, VS Code. Now this is effectively the same as what you guys will be seeing in your Jupyter Hub, or you can use any text editor you want to write your notebooks. Maybe not any text editor you want, but you can use a variety of them. And it just difference is just aesthetic. This is just what I'm used to. That's why it might look a little bit different from what you're expecting to see. And so let's jump straight into it. Okay, so what's the differential equation I'm solving? Well, it's f equals minus kx. We all know that, so it gives rise to simple harmonic motion. And you could probably perhaps write that better as a equals minus k over m times x, just because acceleration is generally what we use. We don't normally use force that much. And in fact, what I would like to do is write that as a second order differential equation to say, okay, the d2x by dt squared is equal to minus k over mx. And likewise, well, actually, it turns out, sorry, I'm going a little bit fast now because I wrote this in advance, and so I'm kind of firing through it. But computers, generally, the way these differential equation solvers are set up is that you solve only first order equations. And so that's a second order equation. Luckily, you can turn any order equation into a set of first order equations by replacing x there by v. So dv by dt is a first order equation. But unfortunately, v is not, v is also differential. So we need a second differential equation. So we've got dv by dt is equal to minus k over m times x, and the x by dt equals v. And so together, these two first order equations are equivalent to this one second order equation. So these two are the equations we're going to set out to solve. And we're probably actually going to solve them in the opposite order. And the second cell is what all I've done there is I've imported some packages that I know I'm going to use. I know I'm going to use NumPy, I know I'm going to use matplotlib, and I know, of course, that I'm going to use the most important thing, scipy.integrate, and from that I'm going to get solve IVP. And so there's two, IVP just means initial value problem. So in our case, we're saying at t equals 0, here's the condition of our system, rather than say a boundary value problem, so solve BVP, which is what you do is you say, okay, maybe for the heat diffusion equation, you'd have say a metal bar maybe, and then at one end you've got a heat source and at the other end you've got like a heat sink, and you want to look at the distribution of temperature across that bar. That would be a boundary value problem, so you use a slightly different function. So instead we're using an initial value problem, so solve IVP. So how do we use it? So we need to first of all give it, this is how we work out how to use it. So I've got basically, this is how you're going to spend a lot of your time when you're coding is on Google, and we're going to search for the function, and we're going to look at it, how to use it. So it says, okay, given your differential equation, d by dt of a function, and an initial value, so that's your y value at t0, right? This is what it does. And the inputs it takes 3 inputs that are required. So these are positional ones. So this is the first input, the second input, third input to the function. The first one is the function. So this is your differential equation, essentially. This is the function that, this is what the solver is going to do is at multiple times during its operation, it's going to call this function, and it's going to retrieve from that function values for your differential equations. Okay, so it needs to say, okay, at this time, given these parameters, what are the differential equations, and it's going to keep doing that over and over again. So that's why you have to supply a callable function. This isn't an array of data or anything, or a variable. This is a callable function that allows it to call this function anytime it needs updated rates of change, like updated right-hand sides of these equations. The second input is a time span, so it's just a start and end time. So the start time kind of is like these are just, they could be anything. You're in the solar system simulator, generally you're going to use days, and this I'm just going to use an arbitrary number. You can take it to mean seconds, or you can take it to mean hours, or whatever. And it needs an initial state. So the initial state needs, we'll get back to that, but this is the initial state. So all your variables, in our case, we've got position and we've got velocity, are our two variables. They need an initial value. So, okay, let's have a think about how we can create those things. Okay, the first thing is the function. So let's create a function. So let's call it rate of change. So I'm not quite sure what I'm going to have as inputs to it. And I know we're going to be returning some kind of, let's not use y, let's use dy. Okay, so we know we're returning something, our rate of change. So we're going to call this with some number of arguments, and we're going to return a rate of change. Now, the calling signature, what this means is that this is how solve IVP is going to call our function. So our function has to take these as inputs, and it has to take the time, and it has to take then y, which is your other variables. So that's the y you can think of as being the current value of all the variables in your system. So they're a little bit technical, but hopefully you're following along. So let's just put them in as that, even if we're not quite sure what those mean yet. Now, what are we going to return? Well, we've got two things to return because we've got two differential equations. So the first thing we need to return is our acceleration. Sorry, let's put that. There we go. All right, I see why that's not worked. Okay, so the first thing is this. So dv by dt, let's just call that, a, just for simplicity right now. We're going to come back and change this in a bit, but just so I can work through this problem, let's call that a for acceleration, and it's going to be minus k over m. I'm just going to call that km as a constant, times x. Okay? And then the next thing, dx by dt, we're going to call v for obvious reasons. And what's that going to be equal to? Well, this is a little bit tricky. So let's just put v for now, because we're not quite sure what we're going to do here. And then I'm going to think, well, actually, what I immediately see is that these things, because I want this input to be an array, and I want this output to be an array. So what I should do is let's just call that dy. Sorry, let's call it dy1. And let's call this dy0. And hopefully this is obvious as to why I'm doing this, because I'm returning dy, that's my output. Now, so my output is the rate of change of my differential equations. So my first differential equation is the one for my rate of change of position, which is with velocity, and the second one is the rate of change of the velocity, which is my acceleration. So let's just say, okay, so 0 is position, is velocity. This is so I can keep track of it, is that index 0 is the position, index 1 is the velocity. So when I say dy0, that means the rate of change of the position, and dy1 is the rate of change of velocity. Simple. Which means we can also have replacements for this along the same line. So again, y0 is our position, and y1 is our velocity. So now I think I'm done, hopefully. Let's make sure that code is correct. Looks like it's good. So now I've got function rate of change. So now I can call it. Now, what were the other two things I needed to put into solve IVP? So the first one was the t-span. Well, that's easy enough. Let's just call that t-span. Why not? Let's go from 0 to 10. I know I don't know if this is right or not, but we'll find out. Now, and the last thing was our initial values. Okay, well, let's do y0. So our initial values, we need an initial value for both our position and our acceleration. So let's say our position was at 10 and our acceleration was 0. So this would be the full extent of our spring. So we got a spring and we're all the way to one side and we're stationary. So our spring's all the way over here at 10, position 10, and it's not moving. So it should spring back with a negative acceleration back towards the center and oscillate from minus 10 to 10 is what I'm expecting to happen here. So how do we do that? Okay, so we need an output. Let's just call it y. Let's just call it y since that's what we're using most places. So we do y equals solve IVP. Now we need the first argument, remember, was the function. So we pass the function, and then we pass the t-span, and finally we pass initial values. Okay, see if this works. T-span is not defined. Of course, I did not run the cell, so those variables hadn't been created yet. Another error though. dy is not defined. Right, okay, that's no worries, because what I'm trying to do here is I'm trying to put a value into dy0, and there is no dy0, it doesn't exist yet. So you can always do something like that. That always works. You can also do like x. You can always do that. I'm assigning both these values at once, but you can't assign just one part of the array or just one subsection of the array without creating the whole array first. So let's create the whole array first. So this is a numpy function. This just creates an array of zeros. So we should create an array of zeros that's size 2, like that. So this is just going to be 0, 0. So if we were to do this argument here, in that, see, it was just 0, 0. Right. Perfect. So hopefully this will run now. What have we got wrong? Okay, I'm not quite sure. But one thing I have noticed while fixing the previous error is that I never actually set km. So I'm just going to set, so this is a combination of the spring constant and the mass. So it's just k divided by m. So I'm just choosing a pretty arbitrary number there. Spring constant's both. Sorry, km, not minus km. Spring constants. It's fine. Okay, so that was the error. So that was a little bit of a strange one. I couldn't see, it wasn't obvious at a glance what the issue was, but I had noticed that in this piece of code, this line was referring to a variable that does not exist. So that's why that was not right. So what is y? So y contains the output of this function. So let's have a look at what the output looks like. So you can see here, here's all the inputs. Now these first three, I mentioned them earlier, are positional ones. So they are ones, and they're necessary as well. You need all these. And so what they do is that just means first, second, and third is what I mean by positional. So the first argument that you pass the function is this one, and then the second is this one, and the third is this one. And these rest of them are optionals. So this says optional. To set an optional one, instead of doing just typing in, passing in the variable directly, you do, like to pass method, you do method equals. And you can choose between some methods here. I think, again, like I said, we'll probably revisit these methods when I think to talk a little bit about what we mean by RK45 and RK23 and LSODA, etc. Now t-eval, again, we could go through all these, but we're not going to. These are just optional. They're all optional outputs. Now our optional inputs even, as well as you can pass an array of options that contains things like the size of the steps that you want to take. And again, we might revisit exactly how these solvers work. But for now, we're just going to assume they do work. Now, what do we return? So what we return is well, the main ones are t and y. Now, so t would be the time point. So that would be I gave this t-span for t start and t end, but I didn't define actually what points I wanted. I just said, give me something that runs from 0 to 10. I think it was 0 to 10, is that correct? Yeah, 0 to 10. So it'll have created an array now of t's, which are my sort of x values, as it were, and my y values. Now, because I had two equations, I should have two y values. So this should be a ND array of length n, length n points, which is the same length as t, and length n, which is the number of differential equations I was solving. So in my case, it should be 2 by some number that I don't know yet. The rest of it we can ignore for now. Okay, so we've now got this y thing that we know contains our array of times plus array of y. So first thing to do is to just look at what that looks like. And so let's have a look at first times. So what does that look like? Well, it's backwards. Okay, so this is our times out. So it's not a straight line, which you might expect, but there's good reason why. And again, if you come back when we talk about these numerical methods, then we can explain why this is not a straight line. So what we got here is this is the time. So remember we said our start time was 0 to 100, so that's the limits on this. And this is just the entry in the array. You can see it's only done 15 steps to get from 0 to 100, and it started off doing little small steps, and it increased the size, and then it kind of decreased the size a little bit at the end, and it got to 100. Okay, what about, let's have a look at y0, which is our position. Okay, so that doesn't quite look like a simple harmonic motion. Now the first thing is that why is it flat here? Well, because we didn't give it an x-axis. So this is just in terms of the array number, and because as you saw in the previous plot, the step sizes weren't all the same, that's why that's happened there. So that's looking a bit more like it. Still not looking great. Now why is it not looking great? Well, it's not looking great because it's got these very discontinuities. So the way Python works here is when it's plotting is it just draws a straight line between all your points. You could call it a linear interpolation. So that's that. We have got another entry here, which is our acceleration, which is, we plot them both at the same time. We could do that. Oh, why is that going on? Right. All right, so it says x and y must have the same first dimension. We've got shapes 15 and 2 by 15. So that's just because this array is, on its side, as it were. So we can do a dot t, which takes the transpose. So what we've done is taken an array that was like that, 2 by 15, and turn it into an array that's 15 by 2. So that's no worries. Oops, I didn't need to run that again. There we go. So now we got both our plots at the same time against time. So at 0, we can see at time at 0, we've got 0 velocity and a position of 10, which is our initial conditions. And it goes accelerates a negative velocity up to negative 1 or so. And then it starts decelerating as the spring comes back out the other side until it gets to minus 10. Well, it doesn't quite get to minus 10, but again, perhaps it's just because of the weirdness that's happened here. So we can possibly fix that. And then it goes back up and then back down. So how can we fix that? Well, it's taken these really big step sizes because it's quite a simple set of equations. So it thinks, well, actually, I know what's happening here. I know exactly how this line's behaving, so I can take these big chunky steps. I don't need to go 1 second at a time. I can go 20 seconds at a time or 10 seconds at a time or whatever. So we could force it via the max step size argument in solve IVP to take smaller steps, but actually we don't really need to. Something we can do is we can do an interpolation. So what I can do is instead of drawing a straight line between these, I can draw a curve between these, and that'll look much more like the symbol. So how do we do that? So the first things first is we have to create a function. The function that will be used to do the interpolation. This is the way that the scipy interpolator works. Well, actually, first things first is to actually get the interpretation functions. Probably that one. Let's go for that one. So 1D just means a one-dimensional function. So instead of f of x and y, it's just f of x. That's what that means. In our case, our acceleration and our velocity are both just functions of time. So that's a one-dimensional function, which is why we use interp 1D and not interp 2D. So how do we use it? Well, we need to create a function. So let's call that f_int. And we do that by using the interp 1D function we just imported. And we need to give it the x values, which would be our times, y.t. Our x values, which will be y.y. Now what you might notice is y.y, remember, was both the time, both the position and acceleration. So this is actually 2 arrays we're passing it. And it'll create an interpolation for both of them, which is very handy. And now, that's that done. So that should work, yep. So how do we use it? Well, we just call it like any other function. So we can just do like, let's do y query is equal to, okay, let's first of all create. So where do we want the points? Well, let's say we've got 100. Let's do 100 data points. Okay, so this will create an array of 0 to 100. That's what np.arrange does, is it creates an array that spans from 0 to 100. By default, it goes in steps of 1. You can change it. If I did So 0 to 100, I could also do in steps of 0.5. Let's do that. Okay. And then y query is equal to our function. Yeah. Let's do that. Oh, what have we done wrong? X query is not defined. Because I did not type that correctly. So now we've got that done. So y query, we could now do plot. I seem to make the same mistakes over and over again. So let's do plt.plot. That should be an underscore. So what you're is, maybe I'm going a bit too fast, but what I'm doing is I'm reading this error and I'm looking at the corresponding line and saying, well, query is not defined. Well, it was never meant to be defined. It was meant to be X query. What have we got wrong this time? X and Y must have, so this is the same thing as we had before, where we need to do that. So that looks exactly the same. And I know why it looks exactly the same. But what for the sake of you, I shall look up the documentation. Now, what interp1d does, like I said, it takes your X and Y values. But what else? It's got some, just like solve IVP, it's got some optional arguments. Now, the first one is kind, and straight away, we can see what went wrong. It says by default is linear. So what it does by default is it takes your equation, your function, and it draws straight lines between all the points. And then your interpolation lies along that line. And that's exactly what the graph was doing when we plotted it the first time, was it interpolating a straight line between them. So we can choose instead a type of spline curve, which is just type of curve, a cubic spline. Sounds good. That's generally what I would use to do any kind of interpolation. Now, in different circumstances, you might want to use different ones, but as a general purpose thing, you can use a cubic spline. So this is our first optional argument, is kind equals, and we're going to say we want a cubic. So it said let's do cubic for cubic spline. Sorry, that's in the completely wrong function. Let's move that into here. There we go. Hey, now we've got a sine curve. In fact, we've got two sine curves. And so this is so we can explore this data a little bit more. We can say, okay, what would it happen if the spring constant was lower? Maybe you guys can answer this question without a simulation. So let's run all our cells again. Again, we get this weird one. And we get, a lower frequency, which is exactly what we expected if we had a smaller spring constant or a larger mass, because it's k over m, remember, so we could have multiplied our mass by 10 or divided our spring constant by 10. And again, if we go up to a higher spring constant or a lower mass, get a higher frequency. And again, if we do our interpolation, we get this higher frequency, but this time, lovely sine curve. And what you would probably want to do next is you'd probably want to do something like that. So they're in dimensional. So I'm not putting units because they're in dimensionless units at the moment. There we go. Last one I guess we could do is put a legend on there, and so our legend is going to be first pause and then val, because that was the way our arrays were arranged. Remember, 0 was pause and 1 was val. So what I'm going to do now is I'm going to go through this piece of code. I'm going to comment it. So I'm going to write in what each thing does, and then I'm going to do a save my changes, etc. And I'm going to put this file somewhere along with this video. And what hopefully this has been is an introduction to, first of all, what solve IVP does, in this case solving a mass on a spring, but hopefully also just an idea of how to go about solving a problem. I'm glad because I made some mistakes along the way, so hopefully you weren't too embarrassed on my behalf as maybe you're yelling at the screen like, oh, what have you done there? You've done it wrong. But I made some mistakes along the way. We discovered some things that I wouldn't necessarily expect. I wasn't necessarily expecting this to be so jaggy, and that generally this is a lovely result. And then hopefully you can take lessons learned here into your solar system simulator and produce an excellent project. So thank you all.